Hey everyone, welcome back. Today we're tearing into something that is deeply technical, highly complex, and absolutely crucial for the safety of anyone driving a modern electric vehicle. We're looking at a detailed technical source document outlining dual motor controller mode transition failures. Think of this explainer as the ultimate anatomy of an EV disaster, but one that's meticulously prevented from happening every single day. We're going to break down the invisible, microscopic battles happening right inside your car's brain. So you got to ask yourself, what actually happens when an EV motor's brain crashes in a fraction of a millisecond? Okay, let's dive into this because we're entering the incredibly high-stakes world of functional safety and ASIL D standards. That is literally the highest possible risk classification in automotive safety. You see, when a dual motor controller switches between, say, torque control, speed control, or an emergency backup mode, it has to do so flawlessly. Zero margin for error. Because if the software stalls or communication diverges for even a millisecond under high electromagnetic stress, you're risking a sudden torque loss, or even worse, an uncontrollable surge of power. Here's our quick roadmap for this explainer. First, we'll cover the millisecond runaway crisis, then dual-core co-diagnostics, followed by ultimate R&D defenses, zero defect manufacturing, and finally, we'll wrap up with devilish production validation. All right, Section 1, the millisecond runaway crisis. Let's get into it. To really understand the solution here, we have to appreciate the sheer violence of the problem. Modern EV inverters are dynamically switching motor control modes in environments with extreme heat, massive currents, and just brutal electromagnetic noise. The source document lays out a rogues gallery of 4 primary root causes for these failures. First up, multi-core race conditions. Think of this kind of like a high-speed relay race. If the baton isn't handed off perfectly, which engineers call data tearing, you get one processing core operating in the new mode while the other is stuck using data from the old mode. It's just total chaos. Second is ground bounce. Imagine a localized electronic earthquake. When power semiconductors switch, they can generate voltage changes of over 10 kilovolts per microsecond. That massive spike shakes the electrical ground so violently that the system actually misreads its own state. Add in sensorless flux drift, which is basically where the motor's mathematical model gets totally confused during sudden changes, plus unexpected low-voltage power sags that trigger watchdog reset conflicts, and you've got a perfect storm for a runaway crisis. Moving on to Section 2, dual-core co-diagnostics. So how does the vehicle actually fight back when physics itself seems out to get it? Well, keep this number in your head, 60 milliseconds. That is the critical ASIL D fault-tolerant time interval, or FTTI. To put that into perspective, a fast human reaction time is about 250 milliseconds. That means if a catastrophic mode transition failure happens, the car has to detect the fault, diagnose it, and perfectly execute a safe fallback procedure in a blink of an eye 60-millisecond window. All of this happens long before you even realize anything is wrong. To pull this off, engineers implement a super strict hardware transition timer. Think of it as a microscopic tripwire. When the system commands a state change, it starts a 15-millisecond countdown. If it doesn't get a definitive confirmation that the transition is complete before that timer hits 0, it assumes the state machine is stuck in this dangerous transitional limbo. It instantly triggers a diagnostic trouble code, P0AI1F, aborts the transition entirely, and forces a safety protocol. Now, what's really interesting here is how it's handled physically with a heterogeneous doer-checker architecture. On one side, we have the doer, which is the main core. This is your math genius, the one executing incredibly complex field-oriented control algorithms. On the other side is the checker, the safety core. Now, the checker doesn't care about the complex math at all. It acts as an ultra-reliable, hyper-paranoid safety inspector that just relies on the basic laws of physics. If the doer goes rogue and outputs a command that would instantly push the motor beyond safe limits, the checker catches it and physically cuts the drive power in under 100 microseconds. But here's the catch. Cutting power at 12,000 RPM isn't as simple as just flipping a switch. If you just open the circuits, the high-speed back electromotive force acts exactly like slamming the brakes on a massive electrical flywheel. It generates a voltage spike that could literally blow up the inverter. So, the fallback strategy relies on these highly precise steps. First, it blocks the pulse width modulation signals. Then, it instantly triggers a 2-phase short circuit acting as a tiny buffer, followed just 1.5 milliseconds later by a full 3-phase short circuit. It's a brilliant maneuver because it clamps that massive high-speed energy directly inside the motor's stator windings, keeping the delicate DC bus voltage safely under 720 volts. All right, Section 3, Ultimate R&D Defense. We've talked about catching the failure, but through DFMEA, design failure mode, and effects analysis, engineers predict and immunize the system against these chaotic micro-events before a single chip is even built. And at the code and memory level, the defenses are absolutely staggering. They use error correction codes and background checks to prevent random bit flips. And to stop that relay race data tearing we talked about earlier, they use lock-free double buffering. This essentially means the system only ever reads from a completed static data snapshot, using a lightning-fast pointer swap so the data is always 100% consistent. On top of that, a 2D lookup table dynamically compensates for motor inductance changes. This ensures the computer's estimation of the rotor's angle stays within a tiny 5-degree margin of error, even when the motor is roasting at 150 degrees Celsius. And when it comes to hardware design, remember that electronic earthquake we mentioned, the ground bounce? Well, to survive it, the system features a common mode transient immunity, or CMTI, of at least 100 kilovolts per microsecond, paired with a negative 5-volt active Miller clamp. So the crucial point is, this is the massive electrical isolation wall that physically stops the vicious, high-frequency noise of the power electronics from leaking over and crashing the low-voltage brain. Which brings us to Section 4, Zero-Defect Manufacturing. Designing a perfect system is one thing, right? Building a million of them is a whole different ballgame. This requires intense PFMEA, process failure mode, and effects analysis, right on the factory floor. Just consider the super strict limits on solder voiding. Every single one of these controllers undergoes a 3D X-ray inspection, and the standards are ruthless. The maximum allowed total air voiding in a solder joint is just 5%, and a single isolated air bubble cannot exceed 1%. You might be wondering why this level of obsession. Well, because a microscopic air bubble in the solder could slowly crack under the high-frequency vibrations of daily driving, and that leads to a split-second clock failure that brings down the entire controller. Before a unit even leaves the line, it faces end-of-line dynamic fault injection. The factory testing machines literally attack the controllers. They inject dynamic faults to verify that the 15-millisecond tripwire timer functions perfectly every single time. And to make sure those highly tuned software parameters aren't accidentally altered, they completely lock down the calibration data using military-grade SA-256 cryptographic hashes. Finally, Section 5, Devilish Production Validation. Before a design is ever approved for mass production, it enters the ultimate torture chamber. Which brings us to DVP&R. And this brilliantly illustrates exactly what we mean by devilish validation. Just think about the extremes involved here. Engineers run these waters at a blistering 105 degrees Celsius, pinned at 12,000 RPM, and force them to transition modes over 100,000 times continuously. They intentionally drop the low-voltage power while injecting massive electromagnetic interference, up to 200 milliamps of noise. The acceptance criteria? The system cannot falsely reset, the transition time must stay under 10 milliseconds, and the fallback over voltage can never, ever exceed 720 volts. This brutal gauntlet is exactly why driving your EV past a massive high-power radio tower won't cause unexpected acceleration. It's already survived much, much worse. We've seen how ASIL D engineering prevents disasters by manipulating time, software logic, and raw physics down to the microsecond. But it leaves us with a fascinating question. If today's modern EV controllers can catch and neutralize a catastrophic hardware or software failure in just 60 milliseconds, what hidden, microscopic battles will the next generation of fully autonomous vehicles need to win to keep us safe? It's just incredible engineering, and it's happening right beneath our feet every day. Thanks for joining me on this deep dive. I hope you look at your car's brain a little differently now.